This is Physics 1020 and 1090. The lecture is for Wednesday, April 15th. We're in Chapter 30 on nuclear energy, but here in this video 3, we're really done with the chapters and we're going to review for Exam 4. Just a few notes about the final exam. First of all, it's over 4 chapters, although the 4th chapter is really only part of the chapter. It's going to be open book, open note like it was before, but it'll be longer. You'll have 3 hours and you'll have more questions, 20 questions. Again, there'll be multiple choice on WebAssign. And I have put on practice exams on 2 of them. One is up already and another one will probably be up by the time you read this video to practice on the exams. A few notes I want to bring up. First of all, I have figured out how to put figures on the WebAssign exam. So there's a chance that you'll have figures on the exam, just like you'll see some of them on the practice exam. You'll see what I mean when you look at the practice exams. I think it's important that you not only just be able to plug numbers into equations, but you actually be able to look at a plot and get the data off of the plot, understand what the plot's saying, and be able to use that plot to get your answer. There are some limitations for WebAssign that I want to point out. First of all, they don't allow subscripts or superscripts. At least I haven't figured out how to do it, which means I can't really write isotopes like carbon-14 with a superscript 14. So I will, in general, write the isotopes as carbon-14 in the sort of that longhand version. And what that really means is it's equivalent to carbon-14, the 14 being the mass number. So keep that in mind, that's how the isotopes will be written. There's no Greek letters, and it doesn't even allow me to write apostrophes. At least they don't look right when I see them. So Wien's displacement law will just be Wien displacement law on any questions on the exam. Now, a couple things to point out. First of all, I told you should get yourself a periodic table, and it still would be helpful to have a periodic table. But Appendix B in your textbook contains information about a lot of isotopes. It has what you need, the name of the element symbol, and the element atomic number, and some of the common isotopes. So you should be able to get everything you need from your textbook, which you should all have. And also, in Appendix C in your textbook is a collection of the important constants that we're going to be using. Speed of light, Planck's constant, mass and charge of the electron, and so on. So you're welcome to make a list of those constants if you want to have them, but you can also put a bookmark in your book back at Appendix C and be able to get those constants very quickly as you need them. All right. Let's begin with, go through chapter by chapter and remember what we're talking about. Chapter 27. Which was quantum physics. And we began by talking about blackbody radiation. That's going to be an important topic for the exam. 3 things on blackbody radiation you want to keep in mind. First, the Wien displacement law, and that was a relationship between the peak wavelength at which the blackbody was radiating at and the temperature of the blackbody. So a typical question is a star has a temperature of, say, 5,000 Kelvin. What is the peak wavelength at which it radiates? You'll be using Kelvin temperatures quite a bit in this exam. You don't have to worry about converting them to Celsius or Fahrenheit or anything. Well, all our temperatures we'll be dealing with will be in Kelvin. Then there's Stefan's law, and Stefan's law goes back, kind of breaks one rule. Now, I don't usually grab stuff from previous chapters, but Stefan's law is really the total power radiated by a blackbody was discussed in section 11.5.4, so that'd be from the first semester of physics. But you should know Stefan's law, that is, you should know how much total power is emitted by a blackbody. And Stefan's law is just the total power is the product of a Stefan-Boltzmann constant, which is a constant, which you may want to write down in your notes, times the area, times the emissivity, which is usually going to be 1, times the temperature to the 4th power. So that's the total power emitted. And then there's Planck's law. And Planck's law was something that wasn't in the book, so you might want to note Planck's law here. We're not going to actually be doing calculations with Planck's law, but you should at least understand what it is. and you should understand what the symbols are, and you should kind of give a rough idea of what it means qualitatively. And remember, Planck's law described this black body spectrum, so you could relate the properties of this black body spectrum to this formula that Planck derived and its place in the history of development of quantum mechanics. All right, so if you're making a list of things that may not be in our book that you want to remember, Planck's law might be one of them. Then we're talking about the photoelectric effect. The photoelectric effect, you shine light down on a metal and electrons come off and you measure their kinetic energy. And the kinetic energy of the electron is equal to the energy of the photon, HF, minus a work function. That is how much energy it took to pull the electron out of the metal. And here's what the plots of the photoelectric effect often look like. Kinetic energy versus frequency. And at these energies, or these frequencies, there are no electrons released because your energy of the photon is less than the work function. And then you get an increase linearly, which means that this frequency right here, where the increase starts, would correspond to one photon energy would be the work function. So the work function would equal HF0, where that would be the key frequency where this rise begins. And the slope of this line is going to be Planck's constant. So you should be able to get all the information you need from a simple plot like this. So when I said I figured out how to do plots, you could just give you a plot, and you'd have to get the work function from the plot. Okay, so that's the photoelectric effect. Then we looked at the production of X-rays, and we found that in general, if you looked at the X-rays, they were produced with a certain intensity versus wavelength. And for wavelengths lower than a certain minimum wavelength, there was no X-rays produced. That would be where you can't shoot an electron in with a certain amount of energy of the electron, and if that the best scenario is where all that energy gets turned over to an X-ray photon. So that would be the minimum wavelength. So wavelengths above that, you get this kind of spectrum with some characteristic lines superimposed on it. But what we'll most often be interested in is relating the minimum wavelength to the kinetic energy of the electrons. Basically, hc over lambda, the photon energy, is equal to the kinetic energy of the electron. And you can figure out then what the minimum wavelength is going to be produced by that X-ray source. And then we talked about Compton scattering. And just remember what Compton scattering is. You fire an X-ray at an electron. That X-ray has a wavelength lambda 0. That electron gets scattered, and the photon gets scattered off at a different angle and also a different wavelength. It's a longer wavelength that loses some of its energy. So you can relate the change in wavelength, that is this wavelength minus this wavelength, is delta lambda. Change in wavelength is h over mc, that's the mass of the electron, times 1 minus cosine theta. Theta is that angle. Now, you gotta be a little careful on these problems. If I ask you for the wavelength shift or change in the wavelength, you're looking for delta lambda, and that's exactly what you want. But if I'm asking you for the wavelength of the scattered photon, then what you really want is lambda 0 plus this wavelength shift. So you gotta be a little careful what's being asked for. But that's the basic idea of Compton scattering. We also talked about de Broglie wavelength, and that is you can assign wave properties to electrons, and the wavelength of an electron would be h over its momentum, or h is times over mass times speed. That would be the mass of the electron. So the key point is that particles also have wave properties. And the final topic from chapter 27 that we really talked about that will be on the exam is the uncertainty principle. That is, uncertainty in position times the uncertainty in momentum is greater than or equal to h over 4 pi. Oftentimes, the wording of a problem will be something like what, with using the best possible instrument, or what's the minimum product of the uncertainty, and you're going to be looking at an equality instead of inequality. But in general, the uncertainty principle uses inequality. You don't really need to remember anything about Schrodinger's equation and the wave function, except possibly just some qualitative things, like the wave function tells you, the square of it tells you the probability of finding a particle, and that kind of issue. But for the most part, we won't be having a lot of problems about the higher, more advanced parts of quantum mechanics. Then we move on to chapter 28, which was the atomic physics chapter. And the first thing we did is talked about Rutherford scattering. And I want you to understand qualitatively, first of all, what Rutherford scattering is. You fire an alpha particle in to a gold foil, and the alpha particles can be scattered off by an angle theta. They'll fly off, and you can detect them by hitting a zinc sulfide screen. And every time an alpha particle hits, it'll give off a flash of light. And Rutherford came up with a scattering formula. And this formula is also, I don't think it's in the book, so you might want to record it in your notes. We're not going to be doing a lot of calculations with this whole complicated formula, but I do want you to appreciate qualitatively what's going on. In particular, I might ask you something like, suppose you wanted to know the ratio of the number of electrons scattered at 90 degrees to the number scattered at 45 degrees. Well, if you're finding a ratio, you'd put this value for 90 over this value for 45. Everything would cancel except the sign to the fourths. So you're really only getting a ratio of the sign to the fourths for the two different angles. Or I might tell you the ratio of Rutherford scattering for a gold foil versus an aluminum foil. Well, you'd look up the atomic number Z for gold and aluminum. It's squared, and then you take the ratio of the squares to get an idea of what the ratio is of the scattered particles. Or I might tell you do two different kinetic energies for the alpha particle, and ask you then, if you did everything else being the same, if you looked at the ratio of the kinetic energies, one for an alpha particle, say, that came from radium, and one alpha particle that came from polonium, I gave you those two energies, what would be the ratio of number scattered? That'd be inverse proportional to the square of the kinetic energy. That's the only kind of thing I need you to do with the Rutherford scattering formula. It is kind of a mouthful. You might want to keep it in your notes. And then we also did something with the distance of closest approach. If you have an alpha particle, it goes flying in, reaches some distance where it comes to a stop because of electrostatic repulsion, turns around and comes back. You can relate the kinetic energy a long ways away of the alpha particle to the potential energy when it comes to a stop, which would be electrostatic potential energy, Coulomb's constant, charge of the alpha particle, which is 2e, times charge of the nucleus, which is Ze, divided by distance. Not distance squared, this is energy, so distance. And you could solve that for d, and you could find the distance of closest approach. And you ought to be able to do that. And sometimes you can phrase this as Rutherford started seeing deviations from his scattering formula at a certain kinetic energy and a certain atomic number, and that means that you've essentially gotten into where the nuclear force is becoming important, and it essentially tells you the size of the nucleus. Okay, continuing in chapter 28, we talked about the spectrum of hydrogen. We talked about the Balmer formula and a more generalized formula, of which the Balmer formula is a special case, and that's the Rydberg formula. And you ought to understand how you can get the wavelengths of light emitted by hydrogen using those formulas. And then the most important thing, really for the whole chapter, I think, is the Bohr model for hydrogen. And you should know, we did the whole derivation. You should know the basic assumptions that you start with in the Bohr model. You have an electron orbiting around a much heavier proton, and the electron is a distance r from the proton, and it's going with a speed v. And you get that it's electrostatic energy that holds the electron in its orbit. So the force times mass time F equals ma. A is the centripetal acceleration, and F is electrostatic force, Coulomb force. And then Bohr also said that the angular momentum, which is mass times speed times radius, is equal to n h bar. It's quantized. N's an integer. Just to remember, h bar is just h over 2 pi. And n can be 1, 2, 3, 4. Those were the two assumptions. The initial setup of the problem with the F equals ma, and then the assumption about quantized angular momentum. And we did the whole derivation. Probably doing the entire derivation would be a little bit long-winded and hard to say for a multiple choice problem. But you should at least know the different parts of it. And in particular, you end up getting the radius, the speed, and the energy of the hydrogen molecule in the different states for hydrogen. And what's really important is you realize that these energy levels that you predict, if you have a transition from one energy level to another, that the energy is going to be given off as a photon, and that relates the Bohr model up here to the Balmer formula and the Rydberg formula, and basically you can derive those using the Bohr model. And that was one of the big accomplishments of Bohr's analysis. So you should know the Bohr model quite well. And finally, we talked about Henry Moseley and his characteristic X-rays. These are those spikes in the X-ray pattern. And this gets a little complicated because when I was doing the analysis in the video, I said the energy of the photon given off, the K alpha photon, the characteristic photon given off, is equal to z squared times 13.6. Well, the book actually does z minus 1, or you could say this is an effective z squared. That gets a little confusing. I think the book's actually a little more correct in using the z minus 1. So I kind of wish I had in my video. But the bottom line is, if you need this equation, I'll give it to you in a problem. Any problem talking about Moseley. So, unlike other questions where I won't necessarily tell you the equation, that's part of your job to find it, I will always remind you that it's z minus 1. So if I gave you, for instance, the energy of the photon, so this isn't so much the energy levels, this is the energy of the photon given off. If I gave you that, or equivalently, if I gave you the wavelength of that photon, you could find out its energy. And then you could solve for z. Just divide by 13.6 and then take the square root and then add 1. You'd solve for z, and then you can look up and see what element that corresponds to, and you can figure out what element is in the sample that Moseley is looking at. So you really put yourself in the shoes of Henry Moseley and say, okay, here's my wavelength. I'm going to now tell you what the substance was that you were looking at. You should be able to do that. Okay. Then we move on to chapter 29, which was nuclear physics. We spent a lot of time on chapter 29, so let's go over some of the things we talked about. We talked about isotopes. And remember, I won't be able to use subscripts and superscripts, so I will tell you, for instance, uranium-235. Then sometimes isotopes are particularly stable because they had magic numbers. This is number one of the things I don't think was in the book, but you may want to record what these magic numbers are in your notes. And if I were to ask you why a particular isotope was so stable, but and you might notice that either the number of protons or the number of neutrons corresponded to a magic number, that could explain why something was particularly stable. Okay, half-life. We talked about what half-life meant, and we talked about how to find half-lives using the exponential function. So, and the relationship of half-life to the decay constant. So if I told you, for instance, that you start off with, a million particular atoms of a radioactive isotope, and you end up with only 200,000, and this happens over, and that after, say, 3 hours, you could then calculate what the half-life is. Or if you knew the half-life, you could calculate what the fraction remains. You ought to be able to do those problems using the exponential function. Remember, sometimes you have to take the inverse of the exponential function or the natural log. So make sure you're comfortable on your calculator calculating exponentials and natural logs so you can get to half-life. There's a relationship also between the half-life and the decay constant. It involves the natural log of 2 or 0.693, so you want to remember that. Then finally, some of these are cast in terms of radioactive dating questions. So if I told you you were at an archaeological site and I told you the ratio of carbon-14 to carbon-12 in some artifact, and I told you what that ratio is in the atmosphere, I wouldn't expect you to remember the atmosphere ratio, but if I told you that, you could then set up an exponential decay problem. Knowing the half-life of carbon-14, you could figure out how old that artifact is. That's another problem that we went over in the videos you should be able to do. Now, then we talked about alpha, beta, and gamma decay. So alpha decay is when the nucleus shoots out an alpha particle, which is just a helium-4 nucleus, 2 protons and 2 neutrons. That means the nucleus itself goes down by atomic number by 2 and the mass number by 4. Then you have beta decay. Beta decay is when essentially one of the neutrons turns into a proton and it shoots out an electron. So the atomic number goes up by 1 because it's got one more proton. The mass number doesn't change because the neutron turned into a proton doesn't affect the mass number. And the charge is balanced by shooting out the electron. If I want to be real specific, I'll call this beta minus to differentiate it from beta plus, which we'll talk about in a minute. And also then there's gamma decay, where you just are in an excited state of a nucleus and you shoot out a photon. So for instance, technetium-99m decayed to technetium-99. It didn't change the isotope, it didn't change the element, it just went from one state to another and it shot out electromagnetic radiation, gamma decay. So you should be familiar with those 3 types of decay are and how they work. And I might ask you, I might give you an isotope, uranium-235. It decays by alpha decay to what? And you have to know what alpha decay is and figure out what it decays to. Now, sometimes nuclei decay by positron decay. And that is, instead of having a neutron turn into a proton will turn into a neutron, and it will shoot out a positive electron, or called a positron. This is generally called beta plus decay, the plus to differentiate it from beta minus decay. And you should be aware that if I tell you what a typical stable nucleus is for some element, like nitrogen-14, and then I ask you what a nitrogen-12, how is it going to decay? Well, it has too few neutrons to be stable. If it has too few neutrons, it'll probably go by positron decay. Whereas if I said nitrogen-16, it has too many neutrons, that'll usually go by beta decay or beta minus decay. So you should be aware that these two come under different conditions. This one goes when you have too many neutrons. This one goes when you have too few of the neutrons. Nuclear reactions. We talked about a bunch of nuclear reactions, and basically all you have to do is balance the total number of protons and the total mass number. So total atomic number and total mass number on both sides, and figure out usually what one of the missing elements is. And finally, we talked about decay chains, and we didn't do a whole lot with the decay chains, but you should at least be aware that some of the long-lived isotopes like uranium-235, uranium-238, and there's an isotope of thorium, that they'll start an alpha decay, which will then go through another alpha or a beta decay, and it'll start a whole chain of events which will go through usually many steps before it reaches a lead isotope and stops. And that's a typical decay chain. It will produce a whole zoo of different elements, radioactive elements, in a rock containing one of those parents that's either uranium-235 or uranium-238 or thorium. So just be aware that those decay chains exist. You don't have to memorize each individual decay chain. Then we went on to chapter 30, although some of this we talked about in the context of chapter 29. The main topics of chapter 30, really only the first 4 sections we covered. And we talked, I think, positrons were discussed in chapter 30, although we discussed them earlier. We talked about fission, that is the breaking apart of nucleus. And we talked quite a bit about the fission of uranium and uranium-235 with the fissile isotope, not uranium-238. And then we talked about fusion, where you take, say, 2 deuterium isotopes and merge them together and form an alpha particle, and that also gives off energy and is another source of energy. So both fission and fusion give off energy. And we also talked a little bit about nuclear reactors. In particular, we spent a whole lecture or a video talking about the Chernobyl nuclear disaster. And you should understand a little bit about nuclear reactors from that. And in particular, the importance of what the moderator is in a nuclear reactor and how that impacts its stability. Finally, we talked a little bit about the history. And again, I'm not going to hold you responsible for all the history we talked about, but for these 8 scientists, you should be able to know who they are, where they're from, what is their main contribution, what are their main discoveries, their main experiments, their main theoretical models. There's a lot of scientists we discussed that aren't on this list. Those you won't need to know all their data. For instance, de Broglie, Moseley, Röntgen, Becquerel. There's a whole slew of scientists we talked about. These are the 8 that you really are responsible for the exam. We read some quotes out of the book, The Making of the Atomic Bomb. I don't expect you to remember all the exact quotes, but sometimes I would read a quote to re-emphasize a point that we had been talking about. You should be somewhat familiar with those. The Manhattan Project, well, we talked a little bit about how you make an atomic weapon and critical mass and what that concept is and how they had to separate isotopes and how another option is use plutonium and what that is. We talked about some of that. That would be fair game for some simple questions, not really numerical calculations, but some of these questions will be qualitative on the historical sections. And we talked a little bit about the play Copenhagen. We did not say too much about that, but you ought to at least know that was about a meeting between Niels Bohr and Werner Heisenberg, both of who were on the list that you need to know about, and how Heisenberg led the nuclear atomic bomb project for Germany, and Bohr was at least one of the leaders in the Western democracies for nuclear physics, and how they met in Copenhagen in the early part of the war and had a disagreement, and how they made the play based on this. So those are the history items. Mainly, if you just know a few of the important facts about these 8 scientists, you should be fine. Okay, so again, open book, open note test. You'll have 3 hours. You can use the internet if you want. Hopefully, the nice thing about having 20 questions as opposed to 6 is if you miss one by clicking the wrong button, you don't drop down quite so dramatically. It'd be a 5-point drop instead of a 16-point drop. The bad thing is you got 20 questions you got to do, but you have 3 hours to do it, so you ought to be okay. So that is the overall exam and my advice for studying the exam. Next lecture, the next class, we will go over the practice exams that I posted on to prepare you. All right, very good, and we'll work on the practice exams, and then we'll discuss them on Friday.